As you can see in the question, we have a reaction in which N2 is reacting with H2 to form ammonia. Now you can see the equilibrium constant for the above reaction is Kp. And what we have to do is, yes, if we have pure ammonia and it is left to dissociate, then the partial pressure of ammonia at equilibrium is given by which of these relations. And you can see we have to assume that the partial pressure of ammonia is very less with respect to the total pressure at equilibrium. So very interesting question. Let us see how to answer. So first of all, what is happening here is ammonia, or you can say pure ammonia, is basically dissociating here. All right, and we know that when it dissociates, it produces N2 plus 3H2. Although you can see I have not mentioned the states, and it is because the states are already mentioned to you in the equation given to you in the question. All right, so now you can see initially, that is at t equals to 0. Let's assume that partial pressure of ammonia is P1, and we know that for H2 and N2 it will be 0 at t equals to 0. Now at equilibrium, what will happen is, let's assume out of this P1, the pressure reduction in ammonia is, let's say, P0, and for N2 you can see the pressure developed will be P0 by 2 therefore, and for H2 it will be 3 P0 by 2, isn't it? Absolutely. So now you can see at equilibrium, the total pressure, which I am indicating with the help of just P. So P here is indicating the total pressure will be equals to partial pressure of ammonia plus partial pressure of N2 plus partial pressure of H2 at equilibrium. All right. So now you can see here for NH3, let's keep this partial. Okay. Now we know that one thing is given to us in the question, that the partial pressure of ammonia is very less with respect to the total pressure at equilibrium, which means what we can do is we can neglect this value. We can neglect this partial pressure of ammonia here. All right. Why? Because it is very less with respect to the total pressure. Clear? So we can neglect the contribution due to ammonia. So now what we are left with is P is equals to P0 by 2, which is the partial pressure for nitrogen gas, and 3 P0 by 2, which is the partial pressure for hydrogen gas at equilibrium. All right. And when you solve it further, what you will get is 2 P0. This means the P0 value is equals to P by 2. All right. So P by 2, and since units are not mentioned in the question, so we can assume it to be in ATM. All right. So let's assume this much of ATM. All right. So now let's proceed further, and we know that what we have to find out is the partial pressure of ammonia at equilibrium. Now we know that equilibrium constant in terms of Kp for this dissociation of ammonia into N2 plus 3H2 can be written as, let me call it as Kp dash, will be equals to 1 upon Kp. Why? We know that the reaction given to us in the question is N2 plus 3H2 is giving 2NH3, for which the equilibrium constant is Kp. Now since dissociation of ammonia is reverse of this reaction, and which means the equilibrium constant for reverse reaction will be 1 upon this Kp, isn't it? So now you can see 1 upon Kp will be written as partial pressure of N2 into partial pressure of H2 cube divided by partial pressure of NH3 square, isn't it? Now what we have to do is to just put the values. All right, let us do this. So now you can see the partial pressure of ammonia, which is what we have to find out, raised to power 2 will be equals to partial pressure of N2 into partial pressure of H2 raised to power 3. And let me tell you, all these partial pressures are at equilibrium. All right, and divided by, let's see, okay, so it will not be divided, but will be multiplied by Kp. All right. So now let's put the values. For N2 the pressure was yes, it was P0 by 2, and now P0 is equals to P by 2, wherein P is the total pressure. So what I can write is P by 4. And now for H2 it was 3 P0 by 2. That means now it becomes 3P by 4 whole cube, and then we have Kp. Clear? So now you can see what we can write here is 3 raised to power 3 into P raised to power 4, and you can see what else we have is 4 raised to power 4 and Kp. Clear? And this is equals to square of partial pressure of ammonia, isn't it? So now you can see if we take square root on both the sides, what we will get is partial pressure of ammonia. Partial pressure of ammonia will come out to be equals to 3 raised to power 3 by 2. Then P raised to power 2. All right. Yes. P raised to power 2 and then 4 raised to power 2 and Kp raised to power 1 by 2. Also we can write it as partial pressure of ammonia at equilibrium will be equals to 3 raised to power 3 by 2 into P raised to power 2. Now 4 raised to power 2 can also be written as 2 raised to power 4 into Kp raised to power 1 by 2. So this is the expression for partial pressure of ammonia at equilibrium in this particular case. Alright, let us now match with the options. So as you can see, option A says 3 raised to power 3 by 2. Here it is fine, and then Kp raised to power 1 by 2, then P square and 2 raised to power 2. See, this denominator term is not correct. So option A is not the right answer. Moving to option B, wherein you can see the numerator is 3 raised to power 3 by 2, Kp raised to power 1 by 2 and P square, which is fine. And the denominator is 2 raised to power 4, which is also correct, which means option B is the right answer. Let's have a look at option C as well. So you can see in option C, definitely this is not matching with the expression what we have calculated. So this is not the right answer. And then option D is also not matching, so is not the right answer. So the only right answer to this question is option B. Let's have a look at this question. You can see according to this question, what we have to do is we have to find out which of these free radicals is the most stable one. All right. So you can see we have 4 free radicals given to us and we have to find out the most stable one. So let me first tell you, whenever you have to compare the stability of free radicals, then the very first thing that you should look for is the presence of resonance. All right. So now as you can see here, there is no you can say conjugated system present, or you can say out of these 4 molecules, none of these is a conjugated system. So resonance will not be the case in these 4 molecules. All right. And then that means we have to look for some other factor. So let me tell you, once resonance is ruled out, the next thing that you have to think about is the presence of hyperconjugation. All right. And let me tell you, more is the number of hyperconjugating structures for a free radical, more will be the stability of that free radical. All right. And a very basic thing that you know is the number of hyperconjugating structures can be you can say calculated or can be found out with the help of number of alpha hydrogens, isn't it? So we know that if you calculate the number of alpha hydrogens, then eventually you will be able to compare the stability, isn't it? Because more is the number of alpha hydrogens, more will be the hyperconjugating structures and thereby more will be the stability. So let's calculate the alpha hydrogens. So now you can see this carbon is alpha carbon as well as this carbon is alpha carbon. And this contains 3 hydrogen. This is also containing 3 hydrogen. That means in molecule A, you can see we have a total of 6 alpha hydrogens. Moving to the option B, you can see in this case we have 3 plus 3 plus 3, that is 9 alpha hydrogens. So obviously one thing is clear, that option B or you can say the molecule in option B is more stable than the molecule in option A. Alright, so A can be ruled out. Moving to option C, you can see here there is no possibility of hyperconjugation at all. So we can straight away neglect option C. And then moving to option D, here you can see we have 3 alpha hydrogens. So definitely we can clearly say that option D cannot be the answer. And this means only and only option B will be the right answer to this question. Let's have a look at this question. The question is saying if the solubility product of zirconium phosphate is denoted by Ksp and its molar solubility is denoted by S, then which of these relations between S and Ksp is correct? Very basic question. Let us see how to answer. So now you can see here we have a sparingly soluble salt, which is zirconium phosphate. All right. So now what is happening here is this zirconium phosphate, this salt, which is sparingly soluble, you can see when it dissolves in let's say aqueous medium, then it ionizes to give you Zr what, let me correct this, yes, it has to be Zr, let's see this, it is 2 or 4, yes 4, so it will give you Zr 4 plus PO4 3 minus. All right, and now you can see we will get 3 such zirconium ions and 4 such phosphate ions. Clear? Yes. So now you can see if you write the solubility product of this particular salt, then the KSP for this salt can be written as 3S, which is for the you can say which is for the solubility of zirconium ions raised to power 3 into 4S for phosphate raised to power 4. So now you can see clearly what we will get is 3 raised to power 3 dot 4 raised to power 4 dot S raised to power 7, isn't it? This is what we are getting. So now from this we can easily find out the solubility, which will come out to be equals to KSP divided by 3 raised to power 3 dot 4 raised to power 4, isn't it? Now one thing is very clear to us from this entire calculation, and yes, let me tell you, it will be raised to power 1 by 7, isn't it? So now one thing is very clear, the final answer has to be the one wherein the overall power of this KSP upon this value is 1 by 7, isn't it? That means we have to basically look for this power. It has to be 1 by 7. So now let's match with the options. You can see in option A this power is 1 by 6, which means option A can be neglected. Now in option B, if you see this power is 1 by 7, so definitely this 1 by 7 is matching with what we have calculated. So option B is the right answer. Moving to option C, here you can see it is 1 by 9, not possible. And in option D also it is 1 by 7, which means now there is a confusion whether B will be the right answer or D. So let's see which one will be the right answer. So now we need to do the multiplication for this denominator term. You can see 3 raised to power 3 is 27. So KSP raised to power, KSP divided by 27, and 4 raised to power 4 is 256. So now one thing is clear, when you multiply 27 with 256, all right, then obviously you will be going to get a term which is more than 216, isn't it? Which means straight away you can rule out option D, and hence the only right answer to this question is option B. Let's have a look at this question. The question is, which of the following pairs shows opposite trend on moving along the period from left to right as well as from top to bottom in a group? All right, very simple question. Let us read the options. Now option A says atomic radius and electron gain enthalpy, and that to negative value. So let me tell you, as you move from left towards right in a period, then we know that the atomic radius decreases, isn't it? Why? Because of increase in the effective nuclear charge, isn't it? Whereas if you move top to down or top to bottom in a group, then due to the addition of an extra shell, the atomic radius increases, isn't it? So here we know it increases. Clear? Now about electron gain enthalpy, we know that as you move from left to right in a period, the electron gain enthalpy, basically the negative value, increases, and the reason is first thing because of increase in the effective nuclear charge value. All right. So, and secondly, we know that when you try to calculate, secondly, you know that electron gain enthalpy is basically the amount of energy released when an extra electron is added from outside to the valence shell of an isolated gaseous atom. Clear? So obviously more is the Z effective, more will be the attraction force that nucleus is going to you can say exert on the incoming electron, and thereby more will be the negative value of electron gain enthalpy, and hence we know that along the period this value or the negative value increases. And when you move down the group, then what happens is as you move down the group, then the distance between the nucleus and the valence shell increases due to addition of an extra shell. All right. And because of this, what happens is the internuclear force of because of this, what happens is the effective nuclear charge either becomes constant or it decreases as you move down the group. All right. And since the effective nuclear charge is decreasing down the group, or it is remaining constant, then we can say that the addition of extra electron from outside this time is not that negative. Basically is not that favorable, okay, which means the electron gain enthalpy, the negative value will not increase down the group this time. And secondly, the other reason for the same is down the group metallic character increases, and we know that metals are known to lose electrons and not to gain, which also supports the fact that electron gain enthalpy, the negative value decreases as you move down the group. All right. So one thing is clear here, you can see the atomic radius is increasing. All right, and electron gain enthalpy, atomic radius is decreasing as you move along a period, whereas the electron gain enthalpy is increasing as you move along a period. So these trends are opposite, which is what is required. Then let's compare down the group as well. So down the group, atomic radius is increasing, whereas electron gain enthalpy value, negative value, is decreasing. So you can see both of these trends are opposite to each other, isn't it? Which means option A is the right answer. Now moving to option B, it says nuclear charge and ionization enthalpy. See, as I told you just now, the effective nuclear charge or the nuclear charge increases as you move from left to right in a period due to addition of an extra proton, isn't it? So you can see this nuclear charge is increasing as you move from left to right, because like when you move from one group to the other in a period, then there will be an addition of one extra proton. Clear? And moreover, if you see the effective nuclear charge also, then it is increasing. Clear? And then about ionization energy, we know that ionization energy is the amount of energy required to take out an electron from the valence shell of an isolated gaseous atom. Clear? And as we move from left to right, we know that the effective nuclear charge increases, which means now the nucleus is holding the valence electron more tightly. So definitely the ionization enthalpy will also increase. Now since both the values are increasing along the period, the trends are not opposite to each other, isn't it? Which means option B straight away can be neglected. There is no need to further check down the group, and you can say there is no need to further compare along the groups. So now you can see in option C, we have ionization enthalpy, which we know will increase as you move from left to right in a period. And electron gain enthalpy is negative value. We already discussed that it will also increase as you move along the period, which means the trend is not opposite, it is same. So option C cannot be the answer. And option D obviously cannot be the answer. So the only correct answer to this question is option A. Let's have a look at this question. The question is, how many structural isomers will exist for this molecule, which is C4H8O, which are ethers? So all these structural isomers that we have to basically tell about should be ethers with no sp2 hybridized atom. So it should not contain any sp2 hybridized atom. Very interesting question. Let us see how to answer. So whenever you get the formulas and you have to tell the number of structural isomers, the very first thing that you have to do is to find out the degree of unsaturation. Clear? So let me tell you, degree of unsaturation for compounds containing carbon and hydrogen and oxygen is calculated using this formula, which is number of carbon atoms into 2 plus number of hydrogen atoms into -1 plus number of oxygen atoms into 0 divided by 2 plus 1. So now you can see in this case we have 4 carbon atoms, so 4 into 2, plus we have 8 hydrogen atoms, so 8 into -1, plus for oxygen definitely it becomes 0 divided by 2 plus 1. So clearly you can see what is the value that we are getting. We know that 2 into 4 is 8, 8 minus 8 is 0, 0 by 2 is 0, then plus 1, that means the du is coming out to be plus 1. Now what does it mean? Let me tell you. See, when you have du equals to 1, then it means the molecule will either have a ring or it will have a pi bond. Clear? But then we have to neglect all such molecules wherein the sp2 hybridized atom is present, which means we have to straight away neglect all those possibilities wherein pi bond is present. Why? Because even if one of the pi bond is present in the molecule, then any one of the atoms has to have sp2 hybridization, isn't it? So we will simply rule out those cases wherein pi bond is present. That means we are left only and only with those structures that are closed structures or ring forms, isn't it? And that too we have to look for ethers only. So let's start drawing. All right. So first of all, since we have 4 carbons in the molecule, let's draw the ether with 4 carbons first of all. So we know that with 4 carbons, the ether possible is this one. All right. Yes. So this is first structure. The second one, now what you have to do is, since you have created a 5-membered ether with this, wherein 4 atoms are carbon and 1 is oxygen, now you have to start shrinking the ring from 5 to 4, then from 4 to 3. All right, so let's now move on to the 4 membered ring. So you can see in 4 membered ring what we have is this molecule. Second, the third one could be this one. All right, yes. So now you can see this is now done, and now we have to go to the fourth case, wherein we have 3 membered rings. Clear? So now you can see in 3 membered rings we have this possibility. Then the other possibility that we can have is this one. The sixth possibility is let's see this one. All right, so these are possibilities, and let me check what else could be possible. Okay, so the 7th possibility will be, you can see this is a 3-membered ring, that is cyclopropyl ring, and this time it will be like this. All right, yes. So you can also consider this as CH3 group. All right, in fact this is a CH3 group only. So now you can see a total of 7 possible ether structures are there for this molecule. All right, so we can say that the number of structural isomers with that are ethers with no sp2 hybridized atoms in it are 7, which means option A is the right answer.